Okay, if I can start with a maybe light-hearted with some serious connotations. I love the diagrams of the memory tiering with the CPU at the top, and you see the memory growing as we go down. But on a number of the slides, I saw a forking rather than a beautiful tiering. So should we be calling this memory forking rather than memory tiering? Thank you.
Will it help if we do that?
It just doesn't seem very graceful. It's like you've got to make a decision which way to go.
I think Scott actually tried to illustrate that there will be multiple. Let me say it a different way. We are going through this transition for new technology, all of us together. We don't really know what's around the curve, around the bend. As we discover more, if there is need for having a different terminology, we'll create them. We're all inventive. We don't want to limit the possibilities at the beginning. We'll be open to possibilities, but it is very likely, because we cannot all afford to have all different kinds of things, it's very likely we will end up with 2, maybe 3 different discrete points to optimize.
How about if we go to the other side here, the left side, and the gentleman in the black?
So I have a question about virtual addresses and physical memory. So up to now, like the common API was often to be that you map a device file, or basically you tie the virtual address to a specific kind of memory. And I think it's a very limiting factor if you have a very structured data set in which you have many pointers. So like, what is the take on basically disconnecting the virtual address from the physical memory being used to actually store that memory, and so that it can evolve over the time of an application. So, it can be fast memory at one point in time of life of the application and go back to slow memory and go back again too fast, so on and so forth. So.
Thank you, Jerome, for volunteering to help.
So your question's about a virtual address being able to map to different types of a physical address associated with different memory types. Is that correct?
Yeah, so basically, like you have page tables over the time of a lifetime of application. The page table first point to DDR, for instance. Then it can go to HBM because like suddenly it's very accessibly by the CPU. And then later on, like the application is going to work on something else for a while. And so you put that memory back to, I don't know, persistent memory, slower memory. And then further down the road, that data get accessed again easily. So you move it back to DDR. And the lifetime, like decoupling keeping the same virtual address over the lifetime. So you can have structured data set, like many pointers, list, tree, whatever, that don't need to be updated anytime you move the memory around.
So I think he's really asking around, how flexible do you think these systems will be? How flexible are they initially, and how will they kind of evolve going forward too, right? So if you want to try to take a shot at that.
So I feel like the model you're describing is what I would term a operating system managed model, where the operating system is hiding the differences and the physical behavior from the application. Is that correct?
No, not necessarily. You can still provide API to user space that allow the application to select at any point in time. And for this range of virtual address, I think it would be better if you can migrate the memory to this like kind of memory. And so you can have like an evolution of it's really having a disconnect between the virtual address and the memory, the media that is being used to store the data for that virtual address. And it can be done by the kernel in an automatic way, like with, like the kernel can have like a heuristic to try to pick best thing. But I think like in the long term, I think you want to provide application API to the application so that the application that has better knowledge about what's going to happen be able to move things around, but keep the same virtual address.
Okay.
Yeah, so maybe I'll try and comment. So one of the things that we're working on right now in the Linux kernel is to do that at the kernel level with the page manager. So we are actively working on having the kernel decide when and how to reclaim pages and then demote them potentially, and vice versa, right? If a page gets hot, you want to promote it back perhaps into higher bandwidth memory, for example. So that is work that's happening now, at least on the Linux side. And I think Scott's working on something similar. But I mean, I think that is one potential approach to doing it, right? So it becomes basically kernel managed memory. You can have memory-only NUMA nodes. So if you want an API, you can still use the NUMA APIs to bind to a memory-only node, for example, which may be however far away from the local CPU, right? It might be 1 or 2, 3 hops, depending on how you set it up. So at least from our perspective, we expect that to exist, but I don't think that's the only programming paradigm that we can expect. Scott, you want to add anything?
Yeah, I would agree that if I were to look forward in the future, there's likely going to be one or at least two programming paradigms, where one is all system managed, operating system managed. The other one is more of an application managed approach. And from an operating system perspective, we do want to support both types of models, because I think it's going to be depending upon the use cases that there's going to be some use cases that's going to prefer one model over the other.
Yeah, just to point out on that, I don't think you want to be exclusive here. So I think, like you want to take the application first. And if the kernel is about managing resources, so, if the kernel say, well, I'm running out of that resources, still allow the kernel to override whatever the application was asking for.
Yep.
Okay. Can we, let's move to the other side of the room then.
Multiple presentations showed pooled memory approaches, and I think especially CMX showed many different diagrams around that. You mentioned 2 different models. I think one everyone's probably very familiar with. You called it serialized or segmented, where particular blocks of memory are assigned to each coherency domain. It can be dynamically assigned, but they belong to that one coherency domain. You also mentioned concurrent, in which a block of memory may be used across multiple coherency domains, and it could be hardware or software managed, a software consistency. The first one is one that I certainly hear about much more. Maybe a round robin question to each of you. How important do you see that concurrent programming model and that use case? Is it a significant use case in your impression? And what's maybe an example of that use case?
You want to start, maybe let Renew? You want to? Can you hear me? All right.
So I think you were predisposed to the first model, you're saying, right? And I think there is a general consensus within from where I come from is to more towards the second model more so. In the sense that providing access to multiple, what was the right word, hosts or nodes, don't expand. I mean, there is I think the word forking that happened, right? There is a time factor in which coherency domain can be expanded. So you got to be careful how far you extend the coherency domain and then bog yourself down to lose the performance part. And it's better to be done in the software domain beyond a certain number. So the thinking, at least from where we come from, is more on the second category long-term than the first one, although there is the flywheel effect of where industry is, we're thinking is the first one. Examples, to some extent, that's the intuitive and the technical argument. We are still trying to find what are the use case, I would say. I'll be honest about it. I don't think we have got that nailed. So there is a gap there.
Thank you.
So anyone else have similar or different on the panel? Thoughts about?
Yeah, I'd love to hear multiple opinions of.
Rob, that's a very good question. The expediency is the key. Building stepwise approaches to the eventual panacea is the key. What can we do first? The concept of pooled memory was first conceived as being this first step. But after having built that, actually, at least in our PowerPoints or in our brains, you just look at it and you say, well, look, I have a processor that is using pooled memory. This pooled memory in such a place that looks as though another processor, another node could have access to it. And then you ask the question, why wouldn't I provide that? How do I do that today? Today, we do that through Ethernet, for example. We have to go outside. But once we have a fabric tightly connected in a locally disaggregated, for example, system, that, yeah, you can see that instead of so many microseconds, you can go through sort of nanoseconds. You ask that question, and smart people will come around and say, if that's what you want, I can do that. Now, why do you want it? The use cases you're asking. Well, you could think about multiple nodes working on the same block of memory, sharing global shared memory, for example, or moving tokens, control elements, semaphores, or just flags from one process to another process. Those things can be done. Now, if it is software-controlled coherency or hardware coherency is another discussion point, and latency and the number of those things per second will be a key.
So maybe if I paraphrased, classic RDMA applications that are optimized then can be dramatically performance optimized.
Right. Just think of just live migration, for example. You have a particular VM, particular task running on one server altogether, but we have a fabric that we know another server is connected to the same logical storage block or memory block. You want to migrate, well, you just do it through the fabric instead of an external fabric.
That is a killer use case. vMotion is the dominant one from where I come from, and that's the way that thought process is going.
Okay, I think we have 5 minutes or less, so we may not be able to get everyone, but we'll have another panel right after this one. But why don't you go ahead, Aaron, or just alternate.
Thank you.
So.
We have been hearing a lot about the CXL thing, but there are other protocols like OpenCAPI and GenZ, which I want to focus here. So some of the problems or the statements, I think one of the presentation for which Microsoft mentioned is the MapReduce problem, which was solved. There are other protocols like GenZ, which solves it in a different way. So GenZ inherently has a collective operations where instead of having a memory tier, that means you have different levels of memory, you actually distribute the compute, which means you distribute and break the compute pieces and move it closer to the data. Have you explored those options? I know we do not have a stable ecosystem as CXL, but we have other protocols which go beyond CXL and solve a different set of problems. Have you ever explored that, and what are your experiences?
Not yet, actually, from our team, actually. So, but Scott, do you have some experience on that one?
Yeah, I don't believe we've done explorations on protocols such as GenZ or OpenCAPI, but the thing is, from the Azure perspective, we're looking for something that is available on all processor architectures. So if you have protocols that are limited in support, then it's not really an option for us.
Yes, I understand the ecosystem. The challenge what being an ecosystem independent representative here is that ecosystems are generally controlled by the silicon vendors. And if you see, that's the challenge we are facing even right now. So that's where I want to understand how, from a hyperscaler's point of view, because you yourself are your own market, trying to solve that challenge.
Collaboration. You are correct in that smart people have thought of solving the problem perhaps in different ways, solving the same problem. And the ecosystem problems are a problem. As I said earlier, in a large data center, we expect certain level, the customers expect certain level of fault resiliency, performance, cost competitiveness. Now, in large data centers, we really do not have the capability, really, or we're not that big, to solve the problem in multiple different ways. So we have to consolidate on a particular one that solves most of the problems.
So we got 1 minute left. Why don't we do one quick question, hopefully, and then you can follow up, the panel break up, you can follow up with these guys afterwards. And we have another 4 presentations. We'll have some more Q&A after that as well. So you keep your questions in mind. Go ahead.
Yeah, thank you. I have just one simple question for zero infinity. It was really impressive for me, but I think in the future when zero infinity goes really widely, don't you need any hardware support for data scheduling or pre-processing? Do you have any idea? Because actually I was a data engineer, and for me, data scheduling and pre-processing was really painful just only for software. So do you have any idea about it?
Yeah, so I do appreciate the questions. Actually, because the current hardware doesn't have those kind of features, that's why the deep splitting actually Microsoft actually they build up the zero infinity software stack. So, but later on, if the hardware can actually provide more, smart service, I think definitely something to explore. Actually, yeah, agree with the comment. Yeah, thank you.
Okay, I think we're going to do a break now.
Yes.